Okay, real quickly, good afternoon. This is it. I think there's a song about that. So, some of you, two of you, besides those that I've talked to, two of you emailed me, and I can't recall names at this moment, asking if you could take your test on Friday. So a total of 4 people. The 2 people I have talked to, they know who they are good to go. But then there were 2 other people who emailed me, and I do not believe I responded. If you 2 people that have emailed me are still interested in taking your test on Friday, you need to see me after class. And then at that point, it will only be potentially, and you have to have a good reason to take it on Friday, okay? There's got to be a valid reason for taking it on Friday. And at that point, then I will figure out who is taking it on Friday. But as of right this minute, 60 of you approximately will be taking it. 59 of you will be taking it on Wednesday, and 2 of you will be taking it on Friday. The other 2 I will talk to individually after class. But that is, as of right now, I expect to see 59 of you on Wednesday at 3:45 to take your final. If you have a grade such that in order for you to pass the class, you would have to make 130 points. The final is only worth 125 points. So you need to see me also. And let's talk about your need, okay? So if there's any questions about that, we'll talk about it after class. As far as what is on the final, that's all on Blackboard. And so the number of questions, the number of comprehensive questions, all of that is already on Blackboard and has been for a while. Today at the end of class, we are going to go over what we have time for on this practice problems that I printed out for you or sent you an email about. If you did not copy this, take a copy. I have several copies here. I don't have 60 copies, but I think there should be enough for everyone who did not copy it. So we will talk about that. Toward the end of class, we will have time to discuss that. All right, tonight we want to finish up with our organic and biochemistry. And to do that, what I will be talking about, I will finish up this section on amines and amides, and then we are going to get into the biomolecules. And the biomolecules are pretty much where we start to pull together the functional groups along with the body, which is really biochemistry. I mean, that's the chemistry, in the body. That's where we're dealing with the biomolecules mostly. And so that's what we're going to do today, and that will finish us up. Before I forget, though, you need a sign-in sheet. Let me pass that out. If you're here from the 8 o'clock class, please see me after class, and I'll have you sign the sheet as well. All right, so epinephrine. Epinephrine is adrenaline, commonly called adrenaline. And it is, what functional group do you think it has? Tell me about the name. Think it's an amine? You're right. It is an amine. It's an amine that is synthesized in the adrenal gland from norepinephrine. It's an amine synthesized in the adrenal gland from norepinephrine. Now, when you are going through your notes and studying your notes, I agree it can be overwhelming because we have gone through a lot of material. Honestly, I think for me and for you, the study practice problems that I've prepared for you probably is going to be really helpful. Honestly, for me, it was helpful to kind of reevaluate, am I teaching what I want to teach? Am I teaching what I think they need to know? And it was beneficial for me to sit down and, one, make it out, and then two, today, I actually filled it in. Now, I have not posted it yet, and I honestly am hesitating posting it because I know what some of you will do. You'll simply take mine and look at it. Or you'll take mine and copy it, which will be a step above taking mine and looking at it. What I really want you to do is make it out yourself. Because what will help you to study for this test is to fill it in alone. Then, after you have done everything you can to fill that in, then go back and look at mine and see if I think and you think the same things are most important. Because that's where, if you take the time to really sit down and fill that out, you will be, this is what you would have to do, in my opinion, to sit down and fill that out. You have to have an extremely good memory, or you will have to be sitting at a table like this and all your notes spread around you, and you're going to go through that first page, or I can't remember, yeah, the first page has the functional groups on it, and so you're going to be sitting there going through that first page, and you're going to be just, okay, yeah, here's that, and so I'm going to start there, but now I think she talked about those over here too, and then you're going to be, that's what I want you to do. That will help you study more than anything. If you simply just take mine and look at it and say, oh, I've studied for the test, then good luck on the test. If you take mine and you just recopy it, well, better luck on the test. But if you'll sit down and really pour over it yourself, I think it will help you tremendously. Now, what are you going to gain from doing that? You're going to get the big picture. That's what I'm hoping you're going to get. One of the big picture items is something that I'm looking at right here. We've talked about amines already. When we talked about amines the first time, we said, okay, it's a carbon with nitrogen. And then we said, okay, yeah, they're more soluble because they have probably some hydrogen bonding, may or may not. Not all of them will have hydrogen bonding, but some of them may have hydrogen bonding. They're probably, they're definitely, I won't say probably, they're definitely more soluble than hydrocarbons. And so you went through those thought processes, and then what did we say some of the common amines were? Already we've talked about some. Say it. Somebody said it. Morphine. Say it louder. Caffeine. Nicotine. Diphenhydramine, HCl, which is what? Benadryl. So we talked about several of these, right? Now, what are you seeing in common? The INE ending? So is that something that's coming up again and again? So just a simple thing like that, I want you to start noticing. Now, the problem is does that mean every time I see INE, or is it going to for sure be an amine in there? Unfortunately, no. But at least it's a starting point, and many of them are truly amines. Here's one, epinephrine. Another one are the albuterol and salmeterol drugs. Now, what are those used for? Say it again. They're inhalers. What do? Dilate the lung passages. Some of you have these. They dilate the lung passages. We call them bronchodilators. They are structurally similar to epinephrine. On the right-hand side of this page, you actually can see epinephrine. And yes, you see the amine. There's the amine. On this side, there's the amine. Is that the only functional group present? No, what else is present? Benzene. And it's overloaded with something else. Alcohols. Look at all those alcohols. I mean, it's got 3 alcohols in there. So it's not just an amine. It has other things as well. But what are we finding out again and again and again about amines? Many of them are stimulants and many of them are depressants. Bottom line, do they affect the same system in the body? Yes. Yes. So that is something to try to keep that in mind. And guys, I understand we are snipping, we're like little bitty snips of organic and biochemistry. What I'm hoping this does for you is give you enough information to, 1, be interested, and 2, as you continue your studies, you'll start to be able to pull things into this that will expand your knowledge. We're not an organic chemistry class. We're very, very limited in it. But I do think it helps you start to develop that interest and maybe the curiosity. Another interesting amide, and this is actually an interesting amide, is penicillin. Penicillin is an interesting amide. So the other actually was an interesting amine, or interesting amines. This one is interesting amide. And penicillin actually contains 2 amide units. It contains 2 amide units. And before we go any further, I want to deal with something else that I've talked about a little bit in the past. And history is not my thing. I'll tell you that right now. I actually am learning a lot of history currently and have for the last few years. But as far as am I a great historian? Absolutely not. And I get really honestly confused in the dates of when things happen. And here was one. Do you remember me talking about Marie Curie? And I couldn't tell you when she lived, right? That was something I couldn't tell you. Now, some of you might know, but I couldn't tell you. I just told you a little bit about her family and, go look her up. Well, in my searching yesterday for help on helping create the study guide I made for you guys, I was doing some looking around and found Marie Curie's name and gathered a little information just to kind of help me. And I remembered it this time because it hit me at the right time, I should say. She was actually born in the late 70s or 80s. She actually won the Nobel Prize in 1911. So if you remember me saying something about the fact that her daughters went on and won some Nobel Prizes and then like the continuation, now let me give you kind of a history. She died in 1934. My dad was born in 1930. He's 87. If she died in 34, her children were probably born in the late 1800s, maybe early 1900s. You follow me? Pierre died in 1906, so her kids were born before 1906. Now, her children are obviously no longer with us, unless they're just really old. I'd say her children are dead, but guess who could be alive? Her grandchildren. And so really, when you think about that, that's pretty recent. To me, that's like pretty recent. Now, the other scenario, penicillin. And you say, well, penicillin is old, 1928. It is old, but guys, my dad was born in 1930. Some of your great-grandfathers were born about the time my dad. So if that is true, my dad could have had penicillin as an older boy, you follow? Because it was developed in 1928. For sure I had penicillin, and for sure you've had penicillin. But really, when you think about it, is penicillin very old? It's not even 100 years old. To me, when you start to put things in that perspective, we have learned a lot of science and chemistry in the last 100 years. It's almost astounding. And you know that, I think, but maybe you're like me, you don't actually think about it. I mean, I think you probably, once you think of technology, you realize it. I mean, cell phones, like I said, when I was in, nobody had a cell phone. What's a cell phone, you know? I mean, I even had a bag phone when I was out of college. So those are really, really new, cell phones are. But just medicine that we take for granted is really relatively new. And that to me is kind of an interesting thing to think of. But what's really interesting to me about penicillin, even more than that, is how it works. So here's how it works. Some of you know this from a micro class. And you help me out if I'm messing it up. You explain better than me. It works by interfering with the synthesis of the bacterial cell wall. It works by interfering with the synthesis of the bacterial cell wall. And here's how. Penicillin deactivates the enzyme needed to make the cell wall. Penicillin deactivates the enzyme needed to make the cell wall. Now, I have a problem, and I bet some of you have this problem too. I have a problem with people. Did y'all ever have a problem with people? Y'all having a problem with people right now? I have a problem with people. My other problems are minor compared to the people problems that I have. Well, it's so interesting to me as I have gotten older, and honestly, the more I've taught chemistry, the more I've taught myself, I think. But it's not just chemistry, I've taught myself through chemistry, which sounds weird, but I get all these correlations just, and I don't know, maybe it's just me, but it's like lots of times when I'm teaching, I think about the correlations that exist between people in real life and chemistry. You know, just like the simple one of when you're close to the nucleus, you're harder to remove, and when you're farther away from the nucleus, you're easier to take. And, you know, that's a simple minor one. But there's so many correlations, and here is one that I find interesting, and I haven't figured this one out yet. So if I wanted to fight something, a person or whatever, you know, if I wanted to fight something, so let's say that I'm mad at this screen. Just to say this, if I'm mad at the screen, what would I do? Me being me, and I'd say most of you are like this, we would just start wailing on the screen. We would just beat up the screen, get a knife, whack it around, you know, whatever, get a bat, use our fists. We would beat up the screen because we're mad at the screen, right? We're trying to kill the screen. You follow what I'm saying? I mean, that's how we fight. I'm mad at you, I'm going to start beating you up. But penicillin hates bacteria, but it doesn't just start beating up the current bacteria that are causing the problem. It like goes out back, goes down, and finds the little bitty baby bacteria that don't have a cell wall. And it just doesn't kill their cell wall. It goes even past that and says, I know what you need to make your cell wall. I'm going to deactivate the enzyme that you need to make your cell wall. I mean, talk about fighting. So it didn't care about the grown-up bacteria. It goes way down here and deactivates the enzyme that makes the cell wall. Now, what does that mean for you and me? That means you're sick. So you get on antibiotic. You get on penicillin or amoxicillin, which I bet 95% of you have had, unless you're allergic to it. So you get on your amoxicillin, and you don't feel better the first day. You don't feel better the second day. About the third day, you start feeling better. By about the sixth day, you feel like you're well. So you quit taking your antibiotic because you know better than the doctor, and I'm well. I don't have to keep taking my antibiotic. Now, let's talk about what's happened going on inside you. The bacteria that were making you sick, did the antibiotic do anything to them? Nope. They kept making you sick. Which bacteria did that antibiotic affect? It affected the ones that were trying to make their cell wall because it deactivated the enzyme that they needed to make their cell wall. So there was a time period there that there were no bacteria that were healthy because they had no good cell wall. But you quit taking your antibiotic and you forgot about the fact that down here there's those little bitty infant bacteria that haven't even gotten to the point of making their cell wall yet. You quit taking your antibiotic. So what about these babies down here? They can grow, and in fact they just flourish. So what happens to you? You get even sicker. Does that make sense on why you're supposed to take the antibiotic for 10 days? Okay? Now, here's me. I wish I could quit fighting that shell and somehow figure out a smarter way to fight. But what's funny is when Alexander Fleming developed or discovered penicillin, did he realize how it worked? Not at all. He just knew it worked. But it's so funny how it works. To me, that is just so funny how it works. And there's a lot of medications, they have no idea how they work. They think they know how they work because a lot of medications have been discovered by accident. Have you heard the term serendipitous? It's just kind of an accidental discovery. And that's how a lot of things have been discovered. So kind of interesting. All right, so what you're seeing in these pictures is this is the penicillin general structure. And what is important here when you're looking at it is to see what? Come on. Who are these? 2 amide units. Now, there's something else. What else do you see? Carboxylic acid, and this was something I only mentioned, I think, once, thiol. Not something major for you to learn, but that is an interesting substance, thiol. So in every one of these, do you see the same basic structure? Look. Is it the same thing in every one of them? And then what's different about penicillin G and amoxicillin compared to this just basic? Benzene ring here and alcohol and benzene, which that whole thing is called what? Phenol. Good. All right. Some other interesting amines we've already actually talked a little bit about, caffeine and nicotine. And these are, as you all know, commonly used stimulants. Commonly used stimulants. And something interesting about them is they're commonly used stimulants that contain nitrogen in a ring structure. We call these alkaloids. We call these alkaloids. So they're commonly used stimulants, caffeine and nicotine. We call them alkaloids because they have that nitrogen in a ring structure. And we can also say that alkaloids are naturally occurring amines derived from plant sources. Naturally occurring amines derived from plant sources. So looking at caffeine and nicotine, what do you see here? Do you see some nitrogens within the ring structure? Sure. Now, do you also see some amides? Yeah, you do see amides. You see amides as well as amines. So here you have an amine, here you have an amine, here you have an amide, here you have an amide. So you do see both. Now, something that I know many of you will want to label is you want to call this an alkene. Is this truly an alkene? Why not? Because the nitrogen. Now, is there an alkene here? Yes, right here is the alkene. There is an alkene present. So there is an alkene. Nicotine also has the nitrogen in rings, and you have the amines. This looks like benzene, but is it really benzene? No, it's a substituted benzene, meaning it has carbon substituted with something else. One of the things that I find some people tend to do, excuse me, you hear people talking about if it's natural, it's safer. That's not true. That is not true at all. I mean, there is I think there's a tendency for us to think if something's natural, it's safer than things that are, unnatural. But, if that's the case, then, why don't we all just use opium? It's natural. I mean, we all should be smoking tobacco and marijuana and, eating lots of caffeine and using opium. We couldn't function, but we'd be all natural. Get naked and tie-dye and whatever, right? No, I'm teasing. But, I mean, do you see my point? How stupid is that to just say it's all natural, so it must be good? Guys, if you have that philosophy, then you've got to look back and say, well, what did people use for medicines before you had medicine? Did they use natural substances? Yeah, they did use natural substances. So are the natural substances chemical things that affect the body? We've already discovered that. We've already seen that. Nicotine and caffeine are natural. They are stimulants. Other things, what was it? The willow bark produced aspirin. I mean, we could go on and on about natural things that were used in medicine. Why don't we all just use natural things now? One, we don't know how, but a big thing is they're uncontrolled. We don't know the amounts to use. What's the benefit? And this is a controversy that people have a lot. Well, marijuana is legal in da-da-da-da-da. Well, marijuana is illegal in Kentucky. Well, if it's legal here, we ought to do it. Medicinal marijuana, it's good. Why aren't we using, blah, 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 blah. But when someone is using medicinal marijuana, it is controlled. And that doesn't mean it doesn't even also have side effects. The problem is the uncontrolled use. And you can do the same thing with nicotine. You can do the same thing with caffeine. You can do the same thing with food. It's uncontrolled. It's when there's no control on it. And I think that's where we have to realize these two are powerfully addictive. All of those that I've talked about are powerfully addictive. Does that mean that synthetic drugs are not addictive? Not at all. Are some synthetic drugs really addictive too? Yes. Yes. The thing about it is I think there's a good saying, and that's moderation. And you need to be under the supervision of someone if you are partaking of legal or illegal, really, because they do affect the body. And I think we forget sometimes how they affect the body. But just kind of as you go through life, I think it's just important to be aware that just because it's natural doesn't necessarily mean it's better, if that makes sense. All right, carbohydrates. Here we are now. And if I had a word, and I did put this word on your notes, on the study guide notes, I would say we're talking about biomolecules. We're starting in our talk of biomolecules. And there are three biomolecules: proteins, carbohydrates, and fats. A long time ago, we talked about the calories per gram for those. What were those? 4 and 4 for who? No, 4 and 4 for proteins and carbs, 4 big C calories and 4 big C calories per gram for both proteins and carbs, and then fats were what? 9 big C calories per gram. Good. And that's on the study guide. I told you to put that down on the study guide. I'm not saying for sure you'll have to have it. That's something when we're talking about the biomolecules. Because every one of the biomolecules can be used for energy. Now that may not be their primary function, but they all can be used for energy. What we want to look at is what makes up these biomolecules and then some of the uses for these other than energy. That's what we're looking at. So we're going to start with carbohydrates. Carbohydrates, we could say, are polyhydroxy aldehydes or ketones. Polyhydroxy aldehydes or ketones. No, it's two different words. Polyhydroxy aldehydes or polyhydroxy ketones. Now I'm going to make you dissect that term. So they're made up of polyhydroxy aldehydes or ketones. What's poly? Many. What's hydroxy? OH. C double bond OH or C double bond O between two C's. Now as you're going through your notes, or if you've been going through your notes, you already can go back in your notes and see when we talked about aldehydes, you put in your notes aldehydes along with alcohols make up the simplest sugars called aldose. Do you remember doing that? Maybe if you've been studying every night you have. And then we said ketones along with alcohols make up the sugars called ketose. Do you remember doing that? So now this shouldn't be too foreign for you. Carbohydrates are made up of many OHs and aldehydes or many OHs and ketones. That's what they're made up of. They are synthesized where? And this is a funny thing to ask this question because you all know the answer. Where are carbohydrates made? Through the process of, I'm going to put the first, synthesized in blank blank through the process of blank. You all know this. Sunshine. So synthesized in green plants through the process of photosynthesis. See, you all knew that. Honestly, though, you just haven't sat down to think about it. Because you think, well, okay, I know I have cereals, carbohydrates, breads, carbohydrates, no steaks, not carbohydrate. Let's see, baked potato, yeah, that's carbohydrate. I mean, you're going through all these things, but you never sit down and think every one of those things that contains a good source of carbohydrates is a what? A plant. They're all plants. Every one of them are plants. And so they are synthesized in green plants through the process of photosynthesis. And carbohydrates may be mono, di, or polysaccharides. One saccharide, two saccharides, or many saccharides. And we're going to look at the important mono, di, and polysaccharides. The monosaccharides are the simplest carbohydrates. Monosaccharides are the simplest carbohydrates, and they generally have 3 to 6 carbon atoms in a chain with many alcohol groups. and I better put this, and they will have a C double bond O. Because the C double bond O between two C's would be the ketone, the C double bond O at the end would be the aldehyde. So they will have many OH groups and they will have that C double bond O. The simplest aldose and the simplest ketose are listed here for you. Now these are the common names. These are definitely the common names. They are not the proper names. And guys, you're not going to have to name these by their proper names. If we were to name these by their proper names, you could sort of figure it out based on what we've done at this point. What's the parent? Prop, and propanol, because it's an aldehyde. And you have, this would make it, since this is going to be considered the parent, propanol would be the parent, then that means these OHs would have to be called probably hydroxy, and because you can't have a propanol, and maybe you can, maybe it's propanol diol, might be, I don't think so. The point is you get the idea of the name based on what you know. I'm not going to expect you to name compounds that have functional groups, a bunch of functional groups like this one does. Now, those practice quizzes that I put on Blackboard, the announcements, those are good. I don't know if you've had time to look at those or not, but you want practice on naming, those are really good practice on naming. Be careful though when you make that quiz on the one that you make the actual quiz and you check the boxes. You could put level 1, level 2, level 3, but don't do that. You put level 1, then look at what it's going to have in it. Because what you don't want to happen is there's boxes and it will say more than one functional group. Uncheck that box. You're not going to have to do those. Just check the box for one functional group. And that way you're practicing things we really are going to do. This one, we would not call it acetone. What do we call the 3-carbon ketone? Propanone, and then it's got these alcohols. Okay? So ours will be different that we're going to actually name. Do you realize, what I want you to get out of this is, do you realize that this is an aldose? Do you realize this is a ketose? Does that make sense? Okay. A little bit more about carbohydrates. Actually going to write it at the top of this. What do you think about the solubility? Why? Because you know they're soluble. Many of them are soluble. You know this already. What is the most common carbohydrate? Say it again. Well, sugar. I would say sugar. Fiber would be the most common on the earth. I didn't really specify where it's most common. Most common in your kitchen, most common in your diet, sugar. Is sugar soluble? Why is it soluble? What's it got a lot of? Say it. You said it. Somebody said it. OH. What did I say they are? Polyhydroxy? What's that mean? Many OHs. Many OHs. So carbohydrates are soluble in water due to OH groups and that polar C double bond O. If that is true, that they have many OH groups and that polar CO, what can you also say about their intermolecular forces? Low or high? Strong, very high. Which means they have high boiling point, melting point. Good. So they have strong intermolecular forces, which means high melting point and boiling point. What is the most abundant monosaccharide? Monosaccharide. Glucose. Glucose is the most abundant monosaccharide. It's glucose. It's also known as dextrose or blood sugar. For some reason, it's called dextrose a lot in the medical field. I don't know why they call it dextrose. I don't know why they just don't call it glucose, but they call it dextrose. So what do you know already about glucose? Is it brain food? What or who have problems with glucose? Diabetics. Okay. So normal blood glucose levels, the book said, are between 70 to 110 milligrams per deciliter. And then it gives you this information about insulin. Now, as we go through here, I want us to start dissecting some of these words. Glucose is what type of biomolecule? Guys, carbohydrate, that's just on the previous page. Carbohydrate. Specifically, what kind of carbohydrate is it? Good. I'm trying to help you learn how to study by asking you these things. And then it goes on to tell us that insulin regulates blood glucose levels by stimulating the uptake of glucose into tissues or its conversion to glycogen. Now, I'm going to go through this a little bit. What's insulin? It's something that regulates. Does anybody have any idea what biomolecule it is? Carbohydrate, fat, or protein? Say it. A protein. It's a protein. Insulin is a protein. Now, we are going to find out right now and again later that proteins have the widest array of functions of any of the biomolecules. Proteins can do lots of things. They have lots of jobs. Like carbohydrates have several jobs, but proteins have even more jobs in the body, which means are proteins extremely important in the body? Yes. Yes, proteins are very important. And one of the important things that proteins do are regulate. They're regulators or controllers. And in this case, insulin controls blood sugar. And it does this by stimulating the uptake of glucose into the tissues to help them have the energy. Or it says, you know what, we got enough glucose going on right here. You need to back down and go to storage. And that storage is called what? Glycogen. Glycogen is a polymer of glucose. I did not see the entire movie Inside Out. I think that's the name of it. Isn't that the name of the movie? Okay. I didn't see the whole movie, but I would love to see a little snip like that of insulin and glucose, because I think that would be so funny to get that picture. Because this was me this morning, okay? This is my picture of how glucose works, or insulin works rather. So this morning, get up, go have my cup of coffee with my little bit of sugar, real sugar, a little bit of half and half, sit down, do my thing this morning. Then after I get done doing that, then I go out and I go down and I feed the animals. Now all I've had, I haven't eaten all night long, right? So I've been fasting all night long, and I have that little amount of sugar, sucrose. I'm going out, going 2 different directions on the farm. I walk about half a mile. It's not very much, but I'm trying to do it. I'm always running behind. So I'm running, not running, but I'm walking as fast as I can. At this point, by the time I get back up to the house, I have to go down a hill, then walk back up a hill. I'm kind of pumping up that hill as fast as I can, but I'm tired. Have I probably already burned up that fresh supply of sucrose? So insulin has said, hey, guys, down in the muscles, there's glycogen down there. It's a polymer of glucose. Remember our polymer? Break them off, break them off. She needs some brain food. She's not thinking straight. She needs some energy to get up this hill. And so I had enough energy to get up the hill because of glycogen. Then, hurry, get ready, take a shower, get ready to go out the door. Don't have time to eat. Grab 2 bananas and hit the road. Go through the morning teaching. I probably used those banana energy up. By the time I'm walking to the car about 11 o'clock, I'm really getting hungry and probably what's happening again. Insulin's saying. Now, let's stop that scenario for a minute and let's say instead of doing what I did, I sat down and I had a big bowl of oatmeal with like 1/4 of a cup of brown sugar in it. Now, at that point, by the time I got to campus, what probably had insulin been telling my body to do? I had extra glucose at that point, didn't I? So what's it doing? Get down to storage. We have way too much overload in the blood. Get down to storage. Does that make sense? And who's telling it to do all this? Insulin. Now, to me, it's funny to think about it that way. And I even had a student once, do you think they really think about that? No, I'm not thinking they think about it. But it's funny to think that's kind of what happens because that's what is happening. It's all done and you don't have to think about it. But your body knows. And so that's one of the things that proteins do in your body. And the carbohydrate gives you the energy. The protein tells it where to go. And when there's too much, it's stored in a polymer. And when there's not enough, it's broken off of the polymer. And so all of these things are trying to put together what we've looked at. 3 common monosaccharides are glucose, fructose, and galactose. And all of these have the formula C6H12O6. So all 3 of these are monosaccharides. But go back to one of the first days we talked about organic chemistry. What could I also call these 3? What are they to each other? Isomers. All 3 of these are isomers. Why can we say that? They have the exact same molecular formula, but they have different structures. And so these are isomers of each other. And this just tells you a little bit about fructose. If you're a honey eater, you'll see a little bit about why honey is so sweet. It's actually twice as sweet as sucrose, but it has the same calories per gram. So looking at these glucose, galactose, and fructose, tell me which are aldehydes and which are ketones. What's glucose? Aldehyde. There's the aldehyde. What is galactose? Good. And what is fructose? Ketone. Now, are they all polyhydroxy? All of them are polyhydroxy, right? Look at all those. I mean, I could just circle OHs all the time. Are all those going to be soluble? Yes. Yes, all of them are going to be soluble. A disaccharide, what do you think it has? I think I've already said it. It's a carbohydrate with 2 monosaccharides. Carbohydrate with 2 monosaccharides. It's a carbohydrate with 2 monosaccharides. And what is, just to write it in your notes, we've already mentioned it, but what is the most common disaccharide? Sucrose. Sucrose, table sugar. Sucrose is the most common disaccharide. What does sucrose contain? What monosaccharides? Sucrose equals glucose and actually fructose. Sucrose is glucose plus fructose. So it is a disaccharide, glucose plus fructose. There are other disaccharides, obviously. That's the most abundant, most common. Lactose is another disaccharide. Where have you heard of lactose? Milk. Lactose is a disaccharide. I don't know, I was like, why am I writing that? It's right there. Don't know why I'm writing that. It's a disaccharide in milk, and it contains glucose and galactose. Now, explain a little bit to you about how these work. If you have a disaccharide, what does it have to do to be used in the body? Break down. And that's called cleave. It has to cleave. It has to break apart. And lactose is broken apart by lactase. What is lactase? An enzyme. So lactose is broken down by lactase, which is an enzyme. And guess what biomolecule enzymes are? Proteins. Enzymes are proteins. So once again, we have proteins involved with carbohydrates. So a protein is breaking apart a disaccharide.
Is that something that's just like naturally occurring in your body?
Lactase is naturally occurring in your body. Now, those people who don't have enough lactase in their body are considered to be lactose intolerant. Now, the good news, if you like milk but you happen to be lactose intolerant, the good news is that many people over time develop the ability to process the lactose because bacteria do it instead of the enzyme. And so they actually can drink milk because they have the extra good bacteria that will cleave that. And so people that are older lots of times can drink milk when they couldn't when they were younger. And so that is something that's an interesting happening as you get older. Anytime you see something that's ose, it's going to be a carbohydrate. Anytime you see ACE, it's going to be an enzyme. Okay, so these are some things you're going to see again. All right, real short little snippet here. It's actually quite a bit of page space, but because mainly I think some of you will find it interesting, but we're not going to spend much time talking about it. Artificial sweeteners. This is what sucrose looks like. This is sucrose. This is sucralose, commonly called Splenda. Now, the one I don't have on here that I know many of you are wanting to know about is stevia, and I don't have it on here. But we're going to deal with the ones I have today. So sucrose, we've already said, is glucose and fructose. And again, this is sugar. This is table sugar. This is Splenda. What's the difference between them? CL. The CLs. The CLs are the biggest difference, and you could go through here and circle what's different. But you've got a CL, an H, another CL, and I think there's something else, or another CL over here. And so there are differences to them. But as far as similarity, flip your page. Are they more similar than any of the others? are these two more alike than saccharin and aspartame are like sucrose? Yes. And this is, again, where I wish I knew more chemistry. You all crack me up. Some of you think I'm just so smart. Oh my gosh, I'm so dumb when it comes to this stuff. Because I look at this and I get like excited to think, hey, these two look a lot alike. They taste similar. I like that. I like when things look alike and they have similar characteristics. What I don't like and I don't understand is how can these two things, I mean, this is making my Diet Dr. Pepper sweet, and this makes real, well, no, that doesn't even make real Dr. Pepper sweet unless you get the old Dr. Pepper. But regardless, they're both sweet, and they look nothing alike. Isn't that weird? To me, that is weird. I don't understand that. I wish I understood that, because I don't understand that. Saccharin down here, this is your sweet and low. This is your pink packet. This is your blue packet. That's your yellow packet. Okay? So all of those packets, that's your white packet, all those are sweet. These two look similar. These two look nothing like that. If this has benzene, for crying out loud, these two have benzene in them. I mean, you would never think they'd be sweet with benzene in them. I mean, that's just weird. I don't understand that. I don't understand that at all. Real quick, to tell you a little bit about aspartame. Aspartame is in pretty much all of the diet soft drinks. If you drink a diet soft drink, you're drinking aspartame. And it is hydrolyzed, meaning broken apart, into phenylalanine. Anybody know what phenylalanine is? Try me loud. Say it. You're close. She says amine. It's an actual, it's a, do I have any exercise science majors in here? I thought I did. Do you all know what it is? You never heard of any part of that word before? Amino acid. It's an amino acid. Phenylalanine is an amino acid. What are amino acids, guys? Building blocks for all protein. Now, why in the world am I asking a exercise science major? Because exercise science majors are going to be dealing sometimes with athletes who are trying to build muscle, who are trying to add amino acids so that they can build more muscle, okay? And that's why I was asking them specifically. But phenylalanine is an amino acid. Okay, so amino acids, that means that you have something that is acting as a carbohydrate but is not a carbohydrate, because does this give energy? What's the whole purpose of artificial sweeteners? To be sweet with no, which means no energy, right? And so this is not giving energy per se, but when it's broken down, it's breaking down into an amino acid. And there are people who have a condition called I always mess this up, phenylketonuria, and they cannot have phenylalanine. Therefore, they cannot have aspartame. And that's why on every diet soft drink, there's a disclaimer that says, this product contains aspartame, da-da-da-da-da, or something to that effect. If you are a phenylketonuria, you cannot have this product. And that's why they're saying that. Okay? Saccharin was actually developed in World War I to help with sugar rationing. It's an old artificial sweetener. Tell me in this structure what functional groups you see. We said benzene earlier. You see an amine and an amide. What's this one? That's the amine. What's this? Amide. And there's two more. And they're hidden. They're hard to find here. Good job. Where's the ester? Bottom? There you go. There's ester. And then there's one more. Carboxylic acid. Right there. Carboxylic acid. Carboxylic acid. Good. So that you're not wondering about this one later, I want to show this to you. What does saccharin have? It has benzene. What's this? Go ahead. Amide. And then this is crazy. It is. It's like a thiol. But what's crazy about it? Anybody see something there that like, it can't do that? It means it has a total of what? 6 bonds? You said we could only have an octet. And you're right, I said you could only have an octet. I wasn't 100% truthful. You can have more than an octet. You don't have to worry about it though. Our chemistry class can only have octets, but the real world can have more than octets. Sulfur is one of those weirdos. It can have 12 electrons. Isn't that crazy? It can have 12 electrons. We didn't do anything like this, okay? But that's why that is like that. It is weird. It's weird. Okay, polysaccharides are carbohydrates that contain 3 or more monosaccharides. And the most common polysaccharides, and you know, I'm not sure that I should say they're the most common, but I mean, it's a very common for sure. We're going to keep it as most common. I've talked about all 3 of these before. I'll tell you this. They are all polymers of glucose. Now, who are they? Glycogen, starch, fiber. What's fiber? Cellulose. Glycogen, starch, and cellulose. All of those are polymers of glucose. We're going to talk about each one of these. The first one we're going to talk about is actually cellulose. We've already talked about glycogen, so I'm not going to talk any more about glycogen. It is where we store our glucose. That's what we use, glycogen. It's our stored glucose. Cellulose is what we call insoluble fiber. That's what we would call insoluble fiber. In our body, we can eat lettuce and not gain weight. Why not? We can't digest it into energy. But there is a certain group of animals that can. What's that name? It's on the paper. Ruminants. Ruminant animals can do that. Now your next question is, what's a ruminant? An animal that has a rumen. Well, what's a rumen? Another stomach. Another stomach. Now, if you want to know, and I'm not trying to gross you out, this is my ag lesson free of charge, probably your last one ever, okay? So, how does a rumen work? Anybody know? I'm hearing. Tell me. Tell me, did you say it back there? You look like you were saying it.
Isn't it when they like eat a lot and so one stomach consumes it all and burns all that stuff and then the other stomach stores it for later? Something like that?
Not exactly. It is an extra stomach. It is an extra stomach. And probably the best way to think of it is as a fermentation tank. Okay? So what happens is the rumen is on the left side of the animal. And like, it's really funny to look at ruminant animals. In the morning, when they've been in the barn all night and haven't had anything to eat, they're thin. Like if I go down there tonight and look at them, they will have this hump. If I go down and look at the goats tonight, they're going to have this hump up here, down here. You got me, okay? So they're going to have this hump. That hump is their rumen that is filled with grass and weeds and sometimes bark, whatever. It's a fermentation chamber. And what happens is the animals have enzymes and bacteria in their rumen that actually take the plant material, it goes into the rumen, and it starts to decompose into glucose. We can't do that, but the ruminant animal can. And one of the ways that it helps them be able to do it is, one, the bacteria and the enzymes are different, but the other thing they do, and this is the gross part, they burp it up, they literally throw it up, chew their cud, swallow it back down. And that process of getting it out, chewing it up, mixing it with more saliva, swallowing it back down, that's the process that helps it break down. If you've ever just sat and looked at ruminant animals in the field, if they're content, you'll see them sitting there or standing there and they're like this. And you'll see this ball rolling around their mouth. That's their cud. That's their cud. The other thing you hear people talking about is their burping or their methane release. You ever heard people talk about, we're having global warming because the cows pass too much gas? I mean, there are people who think that. Okay? Did she just speak in tongues there or what? People think that, though. There are people who think that. Okay? I think she had an out-of-body experience all of a sudden there. That's annoying, huh? That annoys you? Okay. Whew. She's fighting that screen, isn't she? Regardless, we cannot chew a cud. We cannot ferment. Therefore, we can eat lettuce, fill up on it, but not have calories from it. And that's the difference. That's the difference between us. Now, what do we use as our primary form of I just said the answer, of carbohydrates for energy? Starch. Tell me some starch foods. Potatoes, corn, wheat, rice, all those. Now, I had an interesting experience, and I want to say I'm not hypoglycemic, and I do not have any trouble with diabetes. So I cannot speak for people that are in those categories. But I had an experience that I am convinced personally that when your blood sugar is low, starch is a better form of energy for you than sugar. And here's my sugar, meaning sucrose. This is my story. I'm sticking to it. Okay? I actually got super hot one day over the summer. Literally, I've never been this just exhausted, low blood sugar, everything. And so much so I actually came in the house and I literally just lay down on the floor. I was just literally about to not function. I just could barely function. And I told the kids, I said, because I'm thinking, I've got to have some sugar. And I said, get me a popsicle. You know, my thinking was sugar. I need some sugar. They got me a popsicle. It didn't really do any good at all. And I'm like feeling still really bad. And I'm like, I'm not even thinking straight. I mean, my brain was messed up. It was bad. And so I'm like, okay, I got to have something else. And my daughter, don't know why she did it. I don't know what made her go get me this. But I'm like, I've got to have something else. She brings me, we had baked potatoes like the night before. She brings me half of a baked potato, a cold half of a baked potato. She just got out of the refrigerator and she brought it to me. And I'm like, that looks really good, thank you. And so I did. I was like, oh man, that looks great. When it was cold and I was hot. And so I'm sitting there and it was almost instantaneous. I felt better. Now, I'm convinced it was the baked potato starch versus, well, finally the sugar had time to work. Personally, I'm convinced it was the starch. Now, let me tell you why I think it was the starch. Sucrose is made up of glucose and fructose, and it has to be cleaved. It does have to be broken down. So it is going to get broken down, but starch is what? A polymer straight of who? Who? Glucose. It's a polymer of glucose. Remember paper chains? It's a paper chain of glucose, okay? And guess who breaks it down as soon as it gets in your mouth? Amylase. The saliva has amylase. And so it starts immediately, as soon as it hits your mouth and you start chewing it up, it starts breaking it down. I'm convinced if I ever feel that way again, I'm going to go for starch. I'm going to go for starch. I'm not going to go for white sugar product. I'm going to go for starch. Because I'm convinced that got broken down faster than the sugar, the actual table sugar did. And that is the amylase that's doing that. It's actually breaking it down. And what is amylase? Enzyme. And you better tell me again what starch is, because you didn't say that very well. Polymer of glucose. All of these are glucose polymers, okay? All of those are glucose polymers. All right, what is another thing that carbohydrates do that is really interesting? I would say personally, I think this is probably one of the most interesting carbohydrate jobs, most unique one that we don't think of. Blood type. Carbohydrates actually determine your blood type. You may know that. A couple of you? How'd you learn that? Anatomy? Good, good. If you had asked me beforehand what determined blood type, I would have thought of protein. But it's a carbohydrate on a protein that actually determines the blood type. And you can read about that. I'm not going to go through all this. I just want you to realize that it is the monosaccharides that actually determine the blood type. Cannot leave a majority of nursing majors and not talk real quickly about giving blood. If you have not ever given blood, and you have no real reason not to, you should be giving blood. And if you don't know your blood type, you definitely need to know your blood type. Go give blood and they'll tell you. So, who's the universal donor? Specifically who? O negative. And who's the universal recipient? Good job. All right. All right, so we are finished with the first biomolecule, those were carbohydrates. And the next one we're going to talk about are lipids. Now guys, I'm going to just tell you right now, I have already spent a lot of time talking about lipids. I didn't necessarily call them lipids though. Fats and oils. So if you want to go back to that section, or make a note to yourself here to go back to that section when you're studying, you need to do that. You need to go back, because this is by no means a complete analysis of lipids. You have notes on lipids already. So could you say more on fats? Could I say that? Yes. Yes, more on fats or more on lipids. And the one I want to talk about a little bit more to start with are waxes. A wax or wax it's an ester. It's a special ester that is formed from a fatty acid and a high molar mass alcohol. It's an ester formed from a fatty acid and a high molar mass alcohol. What's an ester? C double bond O, O, okay. So do you see the ester in beeswax? All right. So there's the ester. Now then, can you tell me which side of this was the fatty acid and which side was the alcohol? Here? That's the alcohol side. How do you know? Because this is just the O. So this is the alcohol side, and this is the fatty acid side. As you study molecules, I'm hoping you will start to say these things to yourself and be able to say, okay, well now she said that such and such is made up of, well, let me see if I can find that. Let me see if I can find those different parts. That's what you're looking for. Find the different parts. How do you know? Because a fatty acid is C double bond O, what? What's a fatty acid have in it? It's a long chain carbon with a carboxylic acid. So it's a long chain hydrocarbon with a carboxylic acid. What is carboxylic acid? C double bond O, OH. So is this a C double bond O? Yeah. And an alcohol is just simply an OH. What got kicked out of here when this got made? It's kind of funny what got kicked out considering what wax is for. Say it again? No, it couldn't have been a long. This is the fatty acid. This is the long chain. This is the fatty acid side, and this is the alcohol side. What got kicked out when these two formed? It made an ester. Go back again in your head. What did the fatty acid have at the end of it? C double bond O, OH. What's missing? OH. What did the alcohol have? OH. What's missing? Not OH. The O's there. What got kicked out? Water. Think about it. If OH is missing here and H is missing there, what's H and OH?
Water.
And what do waxes repel? Kind of interesting, isn't it? Okay. This is a word we've already talked about. Triglycerides, triacylglycerols. I've talked about this before. I talked about this word is fat. This is body fat. It can also be blood fat, but it's fat. Triacylglycerols or triglycerides are fat. That's what fat is. What do I want to deal with here? Well, first, we've already answered this question tonight, and there's a mess up. This should be a big C. What is it, though? 9. And the metabolism for fats is the same as hydrocarbons. You're going to get water and carbon dioxide when you burn fats. But the part I want to talk about is something interesting that some of you may not know. I didn't know this until somewhat recently. The number of fat cells that we have as adults, and some of you are possibly still making fat cells because you're not quite old enough. Let's say 25. Say 25. But let's say, and I'm using that as a random number. Some of you are still growing and your body is not fully 100% where you're going to be. Most of you are, but there are probably a few of you that haven't reached your ideal or final, I shouldn't say ideal, final height. And so your body's not 100% as an adult maybe. But adults do not make more fat cells. Now, that sounds weird because you mean I can't get fat? No, honey, you can get fat. I can get fat. I can lose fat. I can get fat or thin, whichever. Easier to get fatter than it is for me, thinner. But I'm not making any new fat cells. So what does that mean I'm doing with my fat cells? Expanding them or shrinking them, right? They're either getting bigger or they're getting smaller. Children, on the other hand, are making fat cells. Now, you say, well, why do you even bring that up? Who cares? Well, guys, you all, if you're not a parent, may become parents one day. And I want you to just have an idea about your child and their fat cells. Now, there are a lot of other things I could tell you about kids, but today we're talking about fat cells in your kids, you know? So, what about fat cells in your kids, though? What do you think we should do with children? Tell them they're fat and take away their food? No, that's not what you do. What do? Put them on a diet? No, that's not what you do. You encourage them and you demonstrate to them good eating habits and exercise. Because if they learn as children to stay healthy, all you're doing is, one, teaching them about being healthy the rest of their life, but are you also keeping their number of fat cells less? Yes. Now, personal story, and I should have found this to show it because I don't think anybody ever believes me. When I always struggled with my weight. Back when I was a kid, we didn't have like normal clothes that fat kids could wear. We had to go to Sears and they were called Pretty Plus. I'm not joking, okay? Sears had Pretty Plus size clothes. That sounds weird. Pretty Plus size clothes. So you weren't a size 12, you were a 12 plus. So I wasn't pretty, I was Pretty Plus. But I was fat, or so I thought. I couldn't wear those normal pretty clothes. So I had this stigma, I was fat. Now guys, I can almost guarantee you, even the skinniest person in this room, chances are, had a stage, maybe in 4th or 5th grade, they were a little chubby. Most of us are, because our body's changing. And it's okay. And your kids may get that way. That's okay. Here's what not to do, though. Don't give them a calorie counter book. My grandmother did that. I'm not joking. I'm not joking. I threw the book away just because now I use my FitnessPal, but I have the cover. I tore the cover off and I need to bring it because I know you don't believe me, but it says on the cover something to the effect of, to my Amanda, to my chubby little cookie, maybe if you'll read this you won't be chubby anymore or something like that. I'm not joking. I'm not joking. And that was when I was around that age of, but what's so crazy is I was the kid who, I have notebooks that I kept. I didn't ever throw anything away. I have notebooks that I kept for when I was like 9 or 10 or 11. I had my diet written out. I had that written out. That's how I lived sometimes. I go through stages, of course, because I was constantly. Now, fortunately for me, I didn't become an anorexic or bulimic, but man, I was headed that way. The way I was just totally absorbed by this. I was fat. And I look back now, and when I was a freshman in high school, I was like, I was thin. I didn't think I was, though, because my bottom was still big. And it's but you look at these things and you're like, oh my gosh. Don't do your kids that way. You show them healthy eating habits, they'll learn it. But don't do that to them. But do remember, I have those fat cells because I was a chubby little kid. I can't get rid of those unless I do what? liposuction or cool sculpting. I just saw the ad for that today. I don't know if that works or not, but it's funny. So you can't get rid of them once you have them, but you can shrink them or you can grow them. But just remember that for kids, okay? I just found that really interesting about kids. All right, another really interesting lipid that you guys know about are phospholipids. And these are a lipid that contain a phosphorus atom. It's a lipid that contains a phosphorus atom. I'm not going to read all this. You all already know more than I do about phospholipids. Where are they? Cell membranes. We had a topic on cell membranes somewhat recently. We talked about them being what? Somebody said it, I heard it. Semi-permeable. Where did we hear about a semi-permeable membrane before? Say that again. You said it back there. Dialysis. Dialysis. So, if this almost kind of helps your brain a little bit maybe, where did we used a certain dialysis procedure that used the peritoneum. Peritoneal dialysis, we talked about that. If every cell is covered by a phospholipid, now does that make sense why the peritoneal cavity is such a good filtering mechanism? Does that make sense? I mean, there's a lot of cells in there, right? There's a lot of cells there. And so this explanation, honestly, I have to just admit it, I got on a tangent. There's like over a page talking about this with pretty pictures. You're not going to have to be tested on that, okay? I don't know why I did. I really don't. I don't have a clue. But it's interesting. Yeah. No. I didn't say part of the bottom you do. Part of the bottom is not. But what I'm saying is look at this all deals with, it keeps going down. Yeah, I got on a tangent, okay, in big print. I mean, it's like size 13 or 14 font there. I don't know. I was on a tangent there. But there is something I do want you to get out of this that's really cool. What does this sound like? Now, what am I talking about? I'm talking about the fact that, yeah, you got it, whoever said it. Look at what's going on here. What's going on right here? What's this interior? This is a lipid bilayer. What is this interior? Nonpolar. What's this out here? What's this out here? Now guys, think about something for a minute. What is the number one thing in your body? I'm not overweight, I'm well hydrated, so what is the number one thing? Water. Where are your cells? Floating in water, right? But yet, we've got all kinds of these fat things going on too. So guess what? It's like every cell is covered with this double layer stuff. Both sides of the outside are what? Polar. But the inside is nonpolar. Isn't that wild? And so what does that remind you of? And you said it, a what? Micelle. These sound like micelles. They sound like micelles. All right, and then like I said, I just got excited and interested, and this is interesting, but there's nothing going to be on the test about it. But if you want to read it, it's interesting. But now let's look at the bottom. The bottom is going to be on the test. The bottom is important. So let's talk about the bottom. Steroids. What are steroids? Now, tell me, which biomolecule am I talking about? Say it again. Lipids. This is lipids. This is lipids. We got to lipids when we started with wax. Then we went to triacylglycerols. Then we went to phospholipids. And now we are on steroids. Okay? So steroids are a class of lipids. Follow me? They are a group of lipids that contain 3 6-carbon rings and 1 5-carbon ring. They are a group of lipids that contain 3 6-carbon rings and 1 5-carbon ring. Cholesterol is the most common member of the steroid family. And that may be news to you. You may not have even known cholesterol was a steroid. It is actually the parent steroid. And this is cholesterol. That structure is cholesterol. What do you see there? That's not what makes it the steroid. 6 carbon, 6 carbon, 6 carbon, and what's this one? This is the steroid nucleus. That's the steroid nucleus. So when we say what is a steroid, we're saying that is a steroid. This is a specific steroid called cholesterol. Steroids are extremely common. And you know, early on maybe all you think of steroids is, you know, pump me up. I want some steroids, you know, get me pumped up. Guys, steroids are everywhere. It's amazing. I want to prove to you. This is a random assortment of drug inserts. This is what? A steroid. This is a steroid cream. That is a steroid cream. How do you know? 3 6-carbon rings, 1 5-carbon ring. This is a common steroid called hydrocortisone. That's hydrocortisone. Is it exactly the same as the other one? No, but how do you know it's a steroid? 3 6-carbon rings. All right. Is this a steroid? Is that a steroid? It's upside down, it doesn't matter. Is that a steroid? No, that is not a steroid. At first, though, if you don't look closely, you might think it is. It's not. Why is it not a steroid? It does not have the 5-carbon ring. I love these. These are crazy. Is that a steroid? No, not a steroid. Any of those steroids? What about this one? Is this a steroid? No. Tell you real quickly about this. This one is so funny. A student last semester brought this to me, And the way this was obtained was a little odd, but I probably would do something like this. The person was going by the trash can and saw you know who I'm talking about? And saw a drug insert. And so, he was like, oh, there's a drug insert. Ms. Brooks wanted some, so I'm going to take it. He looks at it, brings it to me. Guess what this is for? The treatment of HIV. He flipped out. I'm talking, and he was like, oh, I went and washed my hands. And he flipped. He absolutely flipped. And it was exciting for us because I'm like, oh my gosh, this is an HIV drug. I mean, it's pretty cool. Sort of. I'm not sure if it's cool or not, but it's cool to know what an HIV drug looks like. So anyway, it's not a steroid. All right. Guess what these are? Yep, birth control pills. Nose spray, fluticasone. You can buy it over the counter. So, are they common? And this one is also a steroid, and it's also a nose spray. So, kind of interesting. They're everywhere. Steroids are absolutely everywhere. It's pretty wild. Steroids are very interesting because they are considered to be a lipid only because of their nonpolar nature and their insolubility in water. So one of the things that determines whether something is a lipid is if it's insoluble in water. And that's why steroids get classified as lipids, is because of their insolubility. And the last thing we want to look at for fats or lipids are the fat-soluble vitamins. If you don't know these, you need to know these. The fat-soluble vitamins are who? A, D, E, and K. And they are stored in your fat. So you need a little fat to store your fat-soluble vitamins in. And they all actually cannot be synthesized in your body except for who? D. And D is the exception. It can be synthesized in the body, and guess from what? And look at that. Isn't that funny? Cholesterol gets such a bad rap. But you have to have cholesterol. If you don't have enough cholesterol, your hormones are out of whack because every hormone is made from cholesterol. So even though cholesterol, you can have too much cholesterol, you have to have enough cholesterol. And I think that's something that's kind of an interesting thing that we don't realize. All right, protein. So that's the last fat or lipid interesting thing we wanted to talk about. The word proteins should have been listed up here, so I'm going to put it up there. What are proteins? We have actually already defined what proteins are earlier in this. What are they? No, an enzyme is a protein. They're what of amino acids? Polymers. They are polymers of amino acids joined together by what? Do you remember what kind of bond it's joined together by? Which is an amide bond. Good. So they're polymers of amino acids joined together by amide bonds. This is something that is very interesting about proteins. As a biomolecule, proteins cannot be stored in the body to be used by the body. Proteins cannot be stored. Are carbohydrates stored as, in the body, they're stored as glycogen. Fats are stored as fat. but proteins are not stored in the body. Now, I need to clarify that because I know somebody's thinking something, I bet, about that. Wanting to say, no, you're wrong. I'll explain. Proteins are not stored in the body. That means they must be consumed daily. Proteins are not stored in the body. They must be consumed daily. Now, proteins have, I've already said this, and we're going to write it. Proteins have the widest array of functions. One of the functions is structure. So, what's this? I know it's my gun, but what is this? It's muscle, which is what? What word are we on? Oh, it's a protein. Well, I thought you said we don't store it. Guys, this is not my stored protein. Now, if you eat me, it is a source of protein for you. What do we eat if we eat animals? We eat the muscle. But this muscle in me is not my stored protein. This is my structure. This is not my stored protein. This is structure. Okay? My nails, my ligaments, my tendons, those are not stored for me to use. I need them for structure. Okay? So if we don't get enough protein, what do we start to do? My muscles aren't going to be this big anymore. Does that make sense? And that's why when you see children who are malnourished, they may be getting enough rice, but what are they not getting enough of? Beans. They're not getting enough protein. And the protein, you can go on and study this more. There are certain essential amino acids that your body has to have to do its functions. And that's why if you are a vegetarian of the certain types that only eat certain things, I don't know all the words, vegan, whatever all those are, there is a certain group of vegetarians that has to eat a supplemental amino acid, and I, off the top of my head, cannot think what that one is. But you are not getting it in your diet, and you're hurting your body if you aren't. Now, a person that is trying to build muscle, or an athlete, what do we have to make sure they get enough of? Protein. So if you're out here working all the time and you're not getting any better, let's say that you're a swimmer and you're swimming but you're not getting any faster because you're not building up any muscle, therefore what should you be looking at? Are you eating enough protein? Because your body has to have a certain amount of protein every day to carry out all of its functions, and if you want to add muscle, you have to add more protein. And that's why you see bodybuilders and people that are serious exercisers, they may be eating 6 or 8 eggs a day and lots of peanut butter. And they're just consuming the protein like crazy to try to build up. And that's why they're doing that. All right, we've already said this, and I'm going to give you what those are. Proteins have more jobs in the body than any biomolecule. And what are those jobs? Let's look at them. What are the jobs? So they have more jobs in the body than any other biomolecule. What do you think those jobs are? Guys, if you're looking at the picture, you can tell me. Structure. Transportation. We already talked about insulin does what? Regulation or control. So let's go through these. Transport, hemoglobin. The fibrous, this would be structure. What's ferritin? What's it? Go ahead, tell me. You said the word. One of the jobs is storage. Actin and myosin are what? We've already listed it. Regulation or controllers. Again, fibrous, that's going to be structure. Myoglobin is what? Storage. There it is again. And hormones. Insulin is a protein that's a hormone. And it's control. So if that's a job, I'll go ahead and list it as a job, but it's a controller. Hormones control. And then energy, of course. They do give us some energy. All of the biomolecules give us some energy, and they do give us some energy. So that is it. You don't have to listen to me anymore, except for another 15 minutes. All right, pull out that study guide. I want to talk to you about using that. I have 2 sets of notes. They are not 100% complete, but you can fight over them after class. One of them is just missing a few things, but overall they're fairly complete. All right, so let's talk about this practice guide. 2 different practice guides you actually have for the functional groups. One of them is on Blackboard already, and I looked at this a little bit today, and this is really interesting. Didn't you pull this one off there? Part of it, but it's not complete. This is what the one on Blackboard looks like. That was already there. It's just to help you learn your functional groups. This has a lot of the same stuff in it that mine does, except they gave you more room to write than I did. This would not be a bad thing to study from. Fill this out, and they give you an answer key on there too. So definitely, if you want to use that, use it, because that is definitely helpful, similar to what I did. So what am I expecting you to do? Like I already said, lay out all your notes and start going through this. That would be a strong suggestion. What am I particularly thinking when I write this? Well, I did it in color. I know some of you don't see the color, but I actually did it in color. And the reason I did that is because I wanted you to note that the alkanes, alkenes, alkynes, and aromatics are all what? Hydrocarbons. So that's something that I would write there. Maybe above it, or put a little line around it and put hydrocarbons. I won't really say a certain word for the alkyl halide, ether, alcohol, and amine, but I will say something about the aldehyde, ketone, ester, carboxylic acid, and amide. What do you think I would say about those 5? C double bond O. That's exactly right. Carbonyl. I would say all of these have a carbonyl. All of those green ones have a carbonyl. Then, as I go through here, I wrote, obviously, the structure, C double bond C, C single bond C, C triple bond C. I did that. That's I think most of you have that down pat, hopefully. The suffix is going to help me in identifying if a name is given. Suffix for alkanes, ane, ene, ein, own. You with me? Those are the things I'm looking for. Guys, every one of these are not going to have a suffix. Because some of these, I didn't tell you the suffix name. If I didn't tell you, you don't need to know it. Some of these, like alkyl halide, is not really a suffix, it's actually a prefix. You say chloro or bromo or iodo or fluoro. That's what that's what you would write in that area. Under the solubility in water, there are certain ones of these that you specifically know about their solubility. Others of these, you're going to write something in relationship to something else. For instance, all of the hydrocarbons are what? Insoluble in water. But down here under, say, ether, you would put something like maybe more soluble than hydrocarbons. But you probably won't have a specific solubility. Now, in alcohols, are you going to have a specific solubility? Yeah, I gave you that. On some of these, I did give you specific solubilities, but a lot of these, it's relative to the other ones. Under the interesting compounds and or characteristics, some of these will have very little, some of these are going to have a lot. I'll be honest with you, when I was doing this earlier today, alcohol, I couldn't fill it all in. I actually had to write some more notes about alcohols because I started looking and I'm like, oh, I want to put that on there and I need to put that, and again, just because I write it on my answer key, that doesn't mean it's on the test. I sat down and did this from memory and pulled through my notes just like I were you doing it. I did not look at the test when I was making this out or filling it in and say, well, now there's going to be a test question over that. I did not do that. Okay? So just because it's on here does not mean 100% it's on the test. Just because if I don't put something on here and it is on the test, that's okay too. Your notes are more important than this. This is practice for you. BP is boiling point. That means boiling point. So write that in if you didn't know what that meant. Boiling point. Now then, under the biomolecules, this is what we've done mainly today. What would you put under the groups often present for fats? What's one we talked about today? Ester. And what else have we talked about being in fats? Lipids and fats mean the same thing, which you might want to put there. Fatty acids. Fatty acids. Fatty acids. So again, I'm not going to fill it out for you now. You need to sit down and do this. There is an extra blank in the middle just because I used the same table skeleton. Just put something there, whatever you want to put there. Under the special molecules like steroid enzyme polymer, again, anything that you think of that you want to write in there. I remember when I was doing this and I was going through my notes, there was something else I put up here, and I can't remember now what it was, that I thought, well, now that's a special molecule. I want to mention that. But I can't remember what it is now. And I don't have my key with me. I left it at home. But again, when you go through your notes, you're going to find things you'll want to add to this. And then just some other thoughts that I wrote down that I wanted to make sure you investigated. And I'll be honest with you, the answer key is going to have nuclear first. I'm actually going to put nuclear first because that is the first chapter we did. And so I'm going to put that first. You need to redo your sapling homework over nuclear. Because I'm assuming many of you, I'm hoping many of you did that like 3 weeks ago when we first talked about it, probably 2.5 weeks ago anyway. It's old. That's in your head a long time ago, really. Go back and redo those questions so that you have that fresh, because you will see more than this on the test. Let's look at this real quick. I want to do one of these with you. I want to do one of these, and I'm going to do what I considered the hardest one. Okay? What do you think on here would be the hardest one? Tell me, left side or right side? Hardest one? Right side. First, second, third, or fourth? That's exactly the hardest one, in my opinion. Find the longest carbon chain. It is 10. But is it a straight across 10? No. How many of you called this the 10 that were the longest carbon chain? I did so also at the first time I did it. Let me tell you how I knew that wasn't right. I looked at that and I started naming it all based on that being the 10, and then I got to this crazy thing. Is that what you all did? Yeah, we must have made something up. I did too. I made something up. I called it like 2-methylpropyl. I think that's about what we did. Something like that's what I did. Because I thought, well, that sounded good to me. I mean, it's got a methyl group, it's a propyl group, so I'm going to just number it, name it. Well, let me tell you something. I got this off one of those quiz sites, so I knew if I got it right or not. And I knew that wasn't right. So I kept doing it, and I kept doing it, I kept doing it. And now, find the longest carbon chain. It's not that one. What's it do? I'm going to start here. Tell me which way to go. Left, down. Good job. That's the longest carbon chain. Now, if you'll do the longest carbon chain that way, you only have true groups that you don't have any goofy names for. Which direction do we number? Do we number from the right side or from the left side? If you start here, let me show you what's going to happen. 1, 2, 3, and that will be what? A methyl. But look on this side. 1, 2, 3, and that's also a methyl, but there is also another methyl. So now which way is the right way? This way. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, who is the parent then? Decane. And guys, I did exactly what I'm doing right now on the answer key. I wrote this and I put decane, and then my process, I mean, you're not seeing me do it, so you don't know my process, but you saw what I did before I wrote the name. I then said, who is this? Methyl. Who is this? Methyl. Who is this? Methyl. Who is this? Ethyl. Who is this? Propyl. Who is this? This is dichloro. Now I'm going to go ahead and put dichloro there. Some of you, I kept hearing you say dimethyl. I did not put dimethyl down here because in the end it's going to be trimethyl. Then you put it in alphabetical order. If you will do what I have just done right here, it will make it so much easier. Because then you say, and I literally start at the back end. I say decane, and then I go in reverse alphabetical order. Who will be next? Propyl. So what number goes with propyl? 4-propyl. Alphabetical. Methyl. But how many methyls? So that's trimethyl. Where are they? 3, 3, 8 dash trimethyl. Yes or no? You with me? And then what? Alphabetical. Ethyl. Who's that? 4-ethyl. And then 7, 7 dash dichloro. Now obviously I would write that on a scrap piece of paper before I wrote it down to begin with, or to be end with, I should say. And guys, go back and do it on your own. Go back and do that one on your own, okay? You with me or not? Does that make sense?
So you number it the way you do because there's two.
I numbered it this way because there are 2 things on the third one, whereas here there was only 1.
So do you just want to get to the first thing? It doesn't like one.
Doesn't matter what it is. No. Guys, listen, because these are some good questions that you're going to have. You want to get to the first substituent, but if, and this is going to be important on these, if a substituent is present and a double or triple bond, the double or triple bond is more important than the substituent. So you start finding the first double or triple bond and let that be a low number. That's going to be what this one is right here. Yes, that's what this one is going to be. This one is dealing with that because you have a substituent and a double bond. This is number 1. This will be number 1. And it's going to go this direction. Yes, it's going to go in that direction. This will be 2. Okay?
I still would have got higher.
Say it louder.
Is the bromine more important
No, that's not, well, yes. Yes, that is more important because you have a choice of bromo or methyl. Bromo comes alphabetically first. It's one each place. There's a double bond each place. B comes before M. Okay?
Will that contradict though, like at any time, like if you go first?
I don't think so on anything I'm giving you.
Okay.
Okay? Speak up, speak up. The way I'm going? Because the double bond is most important. Yes, it's going to be 1, 2, 3, 4. So the double bond here is going to be 4. If you went this direction, it would be 3. I understand what you're saying, but this double bond has to be included between 1 and 2. That's how you call it the 1. That's how you call it the 1-ene. The fact that it's the 1-ene. Okay? Play with it. I probably am not going to give you a diene on the test. I can't promise you I will or won't. I don't think I do, but I can't promise I don't because I haven't looked at the test. But play with it, okay? These are all good ones to practice. They really are good ones to practice for you. And you've also got your sapling. I will. I didn't ever finish that statement. I will post them tomorrow because you've got your homework due Friday at 8. I will post these tomorrow. I may go on and do it tonight. But do them on your own as much as possible. Don't just look at the answers. I will. I'll post them. And I may just do them tonight. Okay? If I have time, I'll do them tonight. If not, tomorrow. Okay? You didn't sign it?
I don't think that's half of them got it.
Okay. Guys, sign the sign-in sheet.